All right, welcome to my lecture on the normal distribution. So, normal distribution is a continuous random variable, so be sure to keep that in mind. And the density function is given by this equation right here, and that applies for any single value of x. However, when you graph this, you're going to see some things that you notice. So it depends on two parameters. One of the parameters is mu, which represents the mean, and the other one is sigma, which represents the standard deviation. So here's some graphs of this normal distribution. So my apologies if this graph is a little bit blurry, but here the graph is of mu equals 0 and sigma is 0.2. Okay, and that's this blue line. The sigma here, that's the smallest out of all these sigmas, and it's the most peaked and sharpest. The others are flatter. So the larger the sigma is, the flatter the curve. So here, sigma equals 1 is the red, sigma equals 5 is this gold, and that's much more flat or much more spread out. Now, the larger sigma represents the data is spread out. There's more variability, more randomness. So here, with very high probability, all the data is between -2 and 2 in the blue curve, but that's not the case for the red or for the gold curve. They have the same mean. So the blue, the red, the gold, they all have their peak at the mean of mu equals 0. So mu controls the center, and sigma controls how spread out or peaked the data is. Okay. Now, the green curve has a different mean, and here we can see that it's shifted. So it has a mean of -2, and it's shifted to the left by -2. So the mean controls the center. Okay. Here's a quick example. So we have that the heights of men in this age group are normally distributed. The average value is 68 and the standard deviation of 5 inches. We want to calculate the probability a randomly chosen man is between 65 and 73 inches. So my random variable x is going to be the height of a randomly chosen man in our demographic. And we're going to compute this probability, right? And we know the density curve, so why not set up the integral from 65 to 73 of the density function? But there's a big problem. This density function right here doesn't have a known antiderivative. You can't find its antiderivative. U substitution doesn't work. Integration by parts doesn't work. So good luck. But notice we're being asked to calculate area, the area from 65 to 73 under the curve. So I can still calculate what this represents. And I can calculate it with Riemann sums, with Simpson's rule, with the trapezoidal rule. Any other of those options will do that. So here, those commands come built in. R will automatically do the Riemann sums for you, or you could use a really good calculator. Okay, that's option A. Option B is to use a table and what's called a z-score. We're going to work through that option first. Okay. So if I want to do option B, I don't want to use R, I'll need this fact. And here's the fact. If x is normally distributed with mean and standard deviation sigma, then this quantity, called its normalization, is also normally distributed and has standard deviation 1 and mean 0. Okay. So here's going to be a table that we use. This is the standard normal table. And there's one in your book, page 679 to 697 to 698. You get a slightly different table, but similar to the one that you're looking at right here. So this is for positive z-values, and this is for negative z-values. Okay, so if I want to calculate this probability, the first thing I do is I standardize everything. When I calculate these numbers, I get negative 0.6 and I get 1. Okay. Now notice the table is for the probability of everything less than z. So that's the cumulative. Okay. So this probability boils down to be the upper limit of integration, which is 1, to the lower limit of integration, which is minus 0.68. So it works just like an integral. Okay. And from the table, I need to look up the value of z being 1. So when I look at z being 1, here's the positive one, and it's 0.8413. So great, I got that one. Then I need for negative 0.68, I need to find that value. And by the way, I believe that that is um, so minus 0.68. Let me just double check something here. So that will be 73 minus 68 will be 5. So that'll be 1. Then this number right here is going to be negative 3. So that should not be minus 0.868. It should be minus 0.6 because that's what this number is right here. Okay, so I need to look for minus 0.68 in this minus 0.6. So I'll go down to minus 0.6. It's 0, 0. So I'll use this first one, 0.2743. And that's how I get that number. Then I do the difference and I get 56%. Now here's how I do it in R. I can take the cumulative, that would be the top, minus the bottom. So this would be the probability of 73 inches right here. And this would be the probability of 68 inches. And I should fill in those values. So the value I want to calculate is for 73, the mean is 68, the standard deviation is 5. Okay. So 65, 68, and 5. That's going to be our probability. So if you just execute that in R, you're going to get the same answer. And this is exactly the same answer for doing the same thing. Okay, so it should be, my preference at least, is to use R. It's a lot quicker, it's a lot more efficient, but if you prefer to use the table, that's completely fine. Okay. So I want to go to R now and just show you. I wrote this function and you'll have this script available. So I'm going to execute this function. You'll need to read through it. It's going to be self-explanatory what it does. It produces a plot. Okay, so that's my function. And I'm going to shade the probabilities that we want to calculate. Okay, so I'm going to fill in my parameters. The mean is 68, the standard deviation is 5, and I want to calculate the probabilities between 65 and 73. My function, by the way, is called plot.normal, and it's going to produce for me a couple of plots. And by the way, I have a package that produces some warnings, so just ignore these warnings. Okay. So let's look at these graphs. So what I've done is I've generated a normal distribution from data, and the data is displayed on this top left graph. And I've overlaid the normal distribution in blue. Okay. You can see that the graph, the histogram, approximates the graph. So my goal is to calculate the area under the curve of the density function in blue, and that's shaded right here. You can see that almost overlaps precisely with the histogram of the normal distribution. But notice it looks a lot like a Riemann sum, so all I'm doing is taking Riemann sums. In fact, that's what the histogram is when I add up those probabilities. But you can see there's a little bit of an overestimate right there if I was to calculate some of the probabilities, right? So it's not exact. I want to calculate the probability between 65 and 73. That's what is shaded, is the area there. Okay. So one thing I want to point out is that the integral from a to b represents the probabilities of the histogram. And histogram is what you're representing. So that's one reason why we integrate. Okay. Now, if I look at the area, which is the probability, is going to be of this curve. That's what I want to calculate. And in blue here, I have the normal distribution as specified. Okay. Now, your tables in R calculate the cumulative probability. That is, they calculate this, everything less than a value. And the value that this represents is the probability that X is less than 73 inches. That's B. So I'm calculating all this red probability. And that's the command that R does, and that's what the table does. And this calculates using a different value in R and the table. This is everything that's less than A. So notice when I take the difference in this red area, I get exactly this area right here. So that tells me I take the difference in the cumulative distributions. And the cumulative distribution is probability X is less than A and probability X is less than B. So I subtract them, I get that middle area. Okay. And that's exactly what we did in the problem. Okay. Now, one thing that I did was I had, oh dear, hopefully this comes back. One thing I had the program do was it calculated an empirical answer. And what it did was it took the total number of observations that were less than B minus the total number of observations that would be less than A, and I divided by the total with this answer right here. Then I printed that answer. Okay. And it got 0.562. It got 0.562 because it was an approximation, right? That was from the histogram, from the data. The theoretical probability that you'll calculate in R and with your table in your book is this one, 0.567. Notice that's exactly the value you get when we did it with the table. And that's no coincidence. Okay, if I just took this right here, I'm going to get 0.567. Right? And this probability right here, that one represents this probability on the bottom left. This one right here represents the probability on the bottom right. And I take the difference to get the top right. Okay. So that's how you can do it in R. And it's kind of connecting like how the histogram works, how the data works with the density, and why we integrate. Okay. But notice the integral is very hard to compute, so we have a nice computer to do it for us. Here's our last problem. And I'll label this example 2. Okay. So our example says the diameter of pipes is manufactured to be 3.25 inches. Every time they produce a pipe, they're hoping it's 3.25 inches. But due to imperfections, every time you produce something, it will be slightly off in the smallest amount, hopefully. The production process does not produce every diameter exactly at 3.25 inches. And hence the diameter of the pipes chosen is a random variable. Okay, no big surprise there. That happens all the time in manufacturing. The mean of the data is 3.25 inches is reasonable. So if you were to take a sample of your data and have an average, it'd be roughly 3.25. And there's some variation, which is 0.04. Now, eventually, if you misspecify a part, like if you produce a part that is 3.35 inches and your customer asks for 3.25 inches, well, that part wouldn't be very useful to your customer. It just wouldn't meet their needs. So the company is going to discard parts if they're larger than 3.3 inches or smaller than 3.2 inches, right? They don't want to cheat their customer, or at least not too badly. And we want to know what proportion of parts must be discarded. Okay. So we're going to use a normal distribution here. And we're going to use the normal distribution because the majority of parts produced meet specification, and you check that with a histogram. Okay. So we'll use R to answer this question. And notice I'm being asked to calculate the probability discarded. It's discarded if it's less than 3.2 or greater than 3.3. If I do the complement rule, that's 1 minus the probability x is between 3.2 and 3.3. So in R, I can just do this. I can do this command. This computes the probability that it meets the specification. That is between 3.2 and 3.3, or at least that it's not being discarded. Okay, so they're saying it's close enough. So that's not discarded. So what's being discarded is the complement, 1 minus that probability. And that's 21% of your parts. So there's probably some refinement in the production process that can be done. Okay, so key point here is that I can use normal distribution, and the command in R is as follows. Let me show you how we do this in R. Okay, so if I want to call this command, let's just copy all of this. I have a mean of 3.25. My standard deviation is 0.04. I want to go from 3.2 to 3.3, and everything looks good. So let's call my function. Those are what I'm going to put into my function. I have some warnings, and one thing is that I'd like to make that a little bit bigger, so I need to resize my graph, which isn't an automatic command, which does defeat the purpose of a function, so I apologize there. It's still not big enough, so just give me another, I think 2 should be sufficient, but maybe I can just take out that argument and it will auto size it. Okay. Almost. So it fit the histogram, but the curve is a little bit off. So this is the normal histogram right here. It's bell-shaped and symmetric. Then when we look in the middle here, we want to calculate that probability to that probability, this nice shaded area. This first command, the first command in R, the first p-norm function calculates this probability. We subtract this probability to get the middle, but what I'm looking for is not the middle, I'm looking for the non-shaded region, so I take the complement and do 1 minus that. That gives me the 21%, which is what's discarded. Okay, so that's a little bit of a summary of how to do these problems. you'll have these notes and these script if you'd like to play with it, but please don't spend too much time on the script. It's not necessarily worth your time, especially if you're not familiar with too many of the commands in R. Okay, thank you very much.